Hey everyone, Mr. Caldwell here. Wanted to give you just a rundown of what exactly work is. So far, we've been talking about work being what happens whenever an object undergoes an energy gain or an energy loss. And we sort of added it into our idea that total energy at the beginning does equal the total energy at the end. But that equation was sort of incomplete at first because we didn't take into account the fact that sometimes things can gain energy, like a rocket taking off starts on the ground with no energy, no potential, no kinetic because it's on the ground not moving. The rockets ignite, and the next thing you know, the thing has both height and energy. So, what we want to get at here today is what is actually a way to calculate work, and what does it depend on? So I'm going to give you sort of an example to think about here. Let's imagine that you have a block and it is sitting at rest. So we've got some mass here, and let's say that the initial velocity is 0. Well, how could I make the block move? I'd have to obviously give it a push. So in order to give this block a little bit of energy, we'd have to exert a force on it. And so it might make sense that if we're talking about how much work is being done, so again, W is for work, the size of the force is going to matter. So we know that we would have to have a force helping us determine how much work is being done. And then there's one other thing that might matter, because a bigger force would give more energy and less force would give less energy. So that kind of makes sense. The other thing that's going to matter is how far we push this thing. So the distance, D, all right? So these are the two things that are going to matter when we are being asked to specifically calculate how much work is being done in a situation. So we're going to say work is equal to force times distance. Remember, force, that's measured in our friend newtons. Distance, we're going to always use the metric system here, and we're going to measure that in meters. And since we said that work is energy gain or loss, work is just energy. And I'm hopeful that you're remembering that energy is measured in joules. All right. So that's actually what work is. Now, you can do work in lots of different ways. So what I wanted to do was go through just a couple quick examples here, hopefully, that will allow you to do the problems that you're supposed to be working on today. So let's imagine that I have a 10 kilogram box, right? And that 10 kilogram box is going to be pushed. 10 kilogram box is pushed across the floor at a constant velocity. We'll talk about what that means here in a second. We'll say that there is a 40 Newton friction force acting on the box. So part A is we want to figure out how much work is done pushing the box 5 meters across the floor. Okay, well, how would we do this? Start by just sort of thinking about a little force diagram here. We know that in order to push this box, I'm going to have to overcome a 40 Newton friction force. So that's going to be fighting me. And so if I push with only 30 Newtons, that's not going to be enough to overcome friction. If I push with 35, that won't be enough. If I push with 400, that would be enough, but that's way too much. I don't need to push that hard. All I need to do in order to get it to move is to just overcome the 40 newtons. 40.01 would be enough to get it moving. And then, because of what we know about the idea of inertia, an object in motion is going to stay in motion. I don't have to push with anything more than 40 newtons. Because the key here is it was at a constant velocity. And if I have a constant velocity, that should, if you go back and think about F equals ma, forces need to be balanced for it not to be accelerating, for the velocity to stay the same. So at this point, work is equal to force times distance. We know that we're exerting a 40 Newton force over a distance of 5 meters. And that is going to be 200 joules. Now we could expand this just a little bit here. And that is what we do to push it across the floor 5 meters. Now part B, a little bit of a different question. What if I wanted to raise this box up? Instead of pushing across the floor 5 meters, excuse me, what if I wanted to raise it up? What if I wanted to raise it up 5 meters? That might be a little bit of a different force. So my box is 10 kilograms. And what you have to remember is that gravity is what's trying to pull this thing down. And the force of gravity is always equal to the mass of the object times the acceleration of gravity, which on Earth is 9.8 meters per second squared. So I would go 10 kilograms here times 9.8 meters per second squared. So what I would have is a force of gravity that would be trying to pull this thing down at a 98 Newton force. So again, same sort of logic. If all I want to do is just raise this thing up, I'm not going to be able to lift it if I only exert 30 or 40 or 50 newtons. But the instant that I exert 98 newtons, just a smidge more than 98 to get it started, and then 98 to maintain its motion, so the force that I would have to exert here would be 98 newtons. So since we're trying to find how much work is done in lifting at 5 meters, how much work is done lifting at 5 meters, we would again go back to our formula and say, all right, here this time, the force and the distance, I'm going to be exerting a force of 98 newtons over a distance of 5 meters. And because it's, well, I can't do that in my head because my brain hasn't quite turned on for the day. That's going to be 490 joules. All right. So those are 2 examples. I'm going to make another video here, give you a couple more examples, and hopefully the combination of these examples and what you already know are going to help you do the problems for today. All right. Thanks so much for paying attention. I hope that you're writing this stuff down, and I will see you guys soon.